AC versus DC coupling. So, for those of us who come from the solar plus storage background or have been around for a while, this is a topic where you see really strong preferences one way or another. You see folks who, just kind of have developed preferences and prefer to do it, one way versus another. Hopefully, what we learned here today, or what we can talk about, is that, there's no one size fits all. Thinking about AC versus DC coupling, a good way to think about that. My analogy here is, it's two different tools. You put two tools in your toolbox, and sometimes you need one and sometimes you need the other. But, very rarely does one tool suit every job. So that's the way I prefer to think about it. You guys know I like to run through the agenda first. So what are we going to talk about? Real quickly, just terms and definitions, do a little background, and kind of talk about why we got here. Try to do why DC couple, why AC couple. Think about some side considerations, maybe some things you hadn't thought about in kind of figuring out which side of the fence you're on, or which tool to reach for. Cover some product and applications, and then have a little time for questions and answers. So if that sounds good, let's get started. So tools in your toolbox, a way of thinking. Former coworker of mine at Schneider Electric had developed this analogy, and I just love it. I think it's so apt. So, ask yourself a question. What's the best format for a car or truck? Front wheel drive, rear wheel drive, all wheel drive, mid-engine? I mean, the answer is really going to be, it depends. It depends on what type of vehicle you're talking about. Depends on what type of transportation you're trying to do. Personal transportation for commuting. Do you have a lot of, cargo you got to carry? Are you an automobile enthusiast and you're interested in, autocrossing, or you're taking your car out on the track? Cost and serviceability, how does that factor in? Really quickly, we can see the answer to the question, what's the best format, is going to be, well, it depends. And you really, it's kind of tedious to go through all these questions for something like, what kind of car do I want? But if you're really trying to get the best, the quote unquote best format, you really need to run through these considerations. Coincidentally, the best answer to this is mid-engine rear wheel drive. So we'll just go ahead and move on. I kid. All right, so definitions. DC coupled or DC coupling, what versus AC coupling versus AC battery. Really what we're talking about in how we couple is, and you see lots of people use slightly different definitions. This is the best set that I've come across, that I've arrived to. And really it has to do with where in the system is the, what I would say the wattage. Where in the system is the wattage from the array being introduced? So in DC coupling, the array is introduced to the system on the DC side of the hybrid or battery inverter, typically via a charge controller to the DC bus. On an AC coupled system, the wattage from the array is introduced into the system on the AC side, typically via a PV inverter. And we'll walk through some examples of this. We'll show some simple block diagrams, and we'll have some illustrations here. AC batteries. So here we're talking about products like Tesla Powerwall 2. Not really either one. You could probably say it's closer to AC coupled, but batteries like this have an onboard inverter, and in most instances are coupled to the home independently of the array. So, you see now some single line drawings where, for all intents and purposes, that AC battery, could be a washer dryer. It's being coupled to the main loads panel almost completely independently of the array. And then sometimes, there's use cases for an AC battery without an array. We typically approach this question from the perspective of people who have been in solar first. But I think there are use cases for a product like this, independent of an array. Crazy to think about, but that application is out there. So those are the definitions. Again, real quickly, DC coupled, we're introducing the array on the DC side of the system. AC coupled, we're introducing it on the AC side of the system. Now you could say, well, everything coming out of an array is DC. This makes no sense, Josh. Really what we mean is where does that wattage, does it have to flow through AC to get to the battery? So maybe that's a better way to think about that. Constantly trying to refresh my assumptions on the best way to explain things, and it changes. But again, how I think about this is, where is that wattage introduced towards the battery, towards the system? DC coupled through a charge controller to the DC bus, AC coupled typically through a PV inverter to the AC bus. So in talking about the different architectures, I feel like it's useful to kind of explain kind of the origins of solar plus storage and kind of how we got here. So running through this left to right, some really old technology that you probably saw in a lot of our really old catalogs, relay-based charge controllers. So real simple devices that kind of had potentiometers to determine high voltage disconnect or low voltage reconnect. And this was basically relays that would close or open a circuit based on voltage, and would allow, when PV resource was there, would allow current to flow from the array through the charge controller into the battery. Big challenge here is twofold, really. You only have, in most cases, a kind of a one-stage charge. The other being you can't run different array voltages than battery voltages. So 12-volt battery, you better have a 12-volt array. We moved to pulse width modulated charge controllers that would allow, you see here, a bulk and a float stage. So starting to add some sophistication. We're still on PWM charge controllers. We're still more or less limited to running 12-volt batteries, 12-volt arrays. And the same would apply to a 24-volt battery and a 24-volt array. On the right here, we see MPPT charge controller. So MPPT standing for maximum power point tracking charge controller. So huge breakthrough here in the DC to DC converter you see here. So allows us to do two things. One, allows us to set a voltage that is presented to an array that will allow that array to produce at its maximum power point. So let's talk about today's modules that are, generally speaking, around 40-volt VOC. So you could present a voltage to that array at 36 or 35 or 37. And your charge controller is going to determine what that voltage needs to be to harvest the most amount of power. So one, you're allowing the array to operate most efficiently. The other point, and I probably should have led with this, is allows you to kind of decouple, if you will, battery voltage from array voltage. So I mentioned most of today's modules want to operate or don't want to operate. Most of today's modules have around a 40-volt VOC. That allows us to use those types of modules with batteries, 12-volt bus, 24-volt bus, 48-volt bus. So we're no longer kind of pigeonholed into a certain array voltage based on our battery. We can decouple those two factors. So MPPT charge controller is really still the cutting edge for charge controllers. I say all this to say, this is the origin of the solar plus storage market. And this is all, DC coupled, if you will. Now you notice we haven't introduced any inversion, but the most straightforward way to connect an array to a battery is through a charge controller. Thus, previously we didn't, I guess you could say, in the roots of our industry, we didn't have the term DC coupled because there was really only one way to do it. So when we add an inverter here, now we've got the ability to invert from DC to AC. You notice that most of these, the flows here from the inverter to the battery are bidirectional. So we've also got the ability to charge from AC to DC. So this is still a DC coupled system because the wattage is flowing to the battery kind of purely through a DC bus. We've got, again, the ability to charge from AC if needed. The AC sources here, from the grid being bidirectional, so we can charge there. We've also got the ability to charge from a generator. Now that flow is kind of unidirectional. You don't want to try to charge your generator. That's generally, as one of my coworkers would say, that's when the magic smoke gets let out. So I say here off-grid DC coupled systems. Generally speaking, this architecture could apply to AC coupled as well. But you see here, there's no grid. There's no meter. You don't have any of those things. So grid-tied DC coupled systems, kind of the next factor here. This is shown here with Connect SW inverters, but there's a whole array of, no pun intended, there's a whole array of inverter chargers that would suit this application. The Outback Radian, the Magnum products, the PTs and the SAEs. Let's see, what else would apply here? Obviously the Outback Radian and the FXR lineup, and a whole wealth of products. So what we're looking at here is really simplified. We've got a grid here on the left. This product does not have cell mode. Most of the other products on the market have cell mode, and thus this flow would be bidirectional. You can pull power from grid to power loads in the home. This would be, depending on how you structure this product, would be a critical load panel or a main load panel. You've then got on the DC side here in blue, you've got an array which will provide power to a charge controller. You've then got a common bus between the charge controller, the inverter charger, and the battery. So, pretty simple stuff. If you've been around, you've probably seen lots of systems designed in this fashion. We'll look at a couple here. This is a system you'll see me present at workshops and road shows around the country. This is a pretty large system in terms of storage, but generally speaking, a pretty good example, pretty common example of what you're going to see. So he's got an FP2 here with two FXR inverters. He's got it looks like two FM80 charge controllers and a pretty high capacity. I don't recall which batteries he went with here, but a pretty high capacity battery bank. 55 kilowatt hours of energy storage. So this is probably an RE2000 or something of the like. Array mounted on the roof, pretty minimal complexity on this one. This system, same general type of architecture, a little more complicated. So this is a, let me count them up here. 1, 2, 3, 4. This is a 6XW cluster. You see here lots of disconnects. You see here on the right the panel board that they're feeding here. And I don't think we're looking at the entire battery bank, but a more high capacity system that's basically off-grid DC coupled. So plenty of examples out there. And I know you guys have seen examples of grid tie DC coupled as well. So we've covered DC coupled a little bit. Here's an example of an AC coupled system. And I threw up here the Sunny Boy and Sunny Island system because, having talked to a number of folks, this is really the first kind of mainstream AC coupled architecture to hit North America, or it was. So kind of working from top down and to the right, we've got our array, and it's worth pointing out here. This is a 1, 2, 3, 4, 5, 6. This is a 12 module string. So right there, one of the first original benefits of AC coupling was being able to introduce longer strings. So in using a grid-tied inverter, you're moving up to a 600-volt DC bus on the array. Previously, and this goes back to kind of pre-2012, I suppose, the charge controllers we used in residential solar plus storage were typically 150-volt bus. So now you're looking at strings usually around strings of 3, and you'd parallel those strings onto a charge controller. And if you needed more than I don't know, say 4,000 or 5,000 watts of array, you'd have multiple charge controllers that you'd then parallel onto an inverter charger. So right now, we clearly see one of the benefits, which is longer strings. Now you'd say, well, what's the benefit of, if I need 12 modules, I could very simply do 4 strings of 3. Maybe I need a second charge controller, maybe I don't. Really, it's going to depend on some other factors that we'll look at later, but just wanted to call that out pretty clearly there. So from the array down through a DC disconnect that may or may not be required now based on the type of grid tie inverter you're using. You've got a one-way power flow to a protected load subpanel, one-way power flow to protected loads, bidirectional flow here from the protected loads to the battery inverter, bidirectional out to the grid, and bidirectional here from the battery inverter to the battery bank. So thinking about our power flows, in cases where array wattage is needed, it's going to come down through the grid tie inverter. When a qualified grid signal is given from the battery inverter, that will power protected loads if there are any. Any excess power will go to the battery inverter. From here, if the grid connection is still live, any excess not required by loads or battery will flow out to the grid. When the grid is down, you still have the remainder of the system operational. If the batteries are full and the array is producing, it will try to go to the loads. If there's no loads and the grid tie inverter is still producing, you've basically got no choice but for that power to flow through here to the battery. Now, when the batteries are full, the grid is down and there's no protected loads, and obviously no other loads in the panel that we're trying to power. That power has nowhere to go, and in most instances, you would then quickly power off the grid tie inverter as quickly as possible, but you can have what we call uncontrolled charge current. So very high level overview of AC coupling there. Let's talk about AC coupling with Outback Radiant. And one of the new things I wanted to make sure I covered here was there's some new firmware out from our folks at Outback Power. You wouldn't normally think that new firmware is something to really be excited about. This has been something that a lot of folks have been eagerly awaiting for a long time. So this is firmware that's going to allow your Radiant to kind of play nicely with your grid tie inverter. And what I mean by play nicely there is your Radiant's now going to modulate the frequency and the shape, if you will, of the AC grid that it presents to the grid tie inverter. So what do we mean by that? We see here some this diagram that I'm showing here comes from the application note that whoa, what happened? Comes from the application note linked here from Outback Power. So in what we're trying to show here in this waveform is you see the wave, kind of nice sinusoidal AC wave, and then we see the wavelength shorten, we see the frequency increase. So the Outback Radiant now has the ability through this new firmware to alter the frequency that it presents to the grid tie inverter. What does that do? Well, we know that grid tie inverters, hopefully we know this, we know that grid tie inverters require a qualified grid to be able to export power. So this goes back to UL 1741 and now UL 1741 SA. A grid tie inverter needs to see a qualified grid, needs to count up over a 5-minute period. Make sure the grid is qualified before that grid-tied inverter is allowed to harvest wattage and produce AC power. Why is that? Well, it goes back to the original intent of protecting line workers, that if there was an outage in a given area, be it planned for service or unplanned, that electrical workers could service that grid knowing that the grid was down effectively. And it's similar to your lockout tagout procedures for servicing of equipment, et cetera. So if that grid-tied inverter does not see a qualified grid, no production is there. So if you've ever worked on systems at the end of a long feeder line off of a transformer, you know that sometimes you see scenarios where the quote-unquote grid in a given area is not a nice, tidy 120/240 at 60 hertz. Sometimes the voltage is high or low. Sometimes the frequency can be really low. In short, you know, the grid-tied inverter needs to see a qualified grid. The Outback Radian without grid and without this new firmware would produce a really clean 120/240 at 60 hertz kind of perfect waveform if it needed that grid-tied inverter to work. When it didn't, it would simply, you know, disconnect. It would basically cease presenting that nice tidy waveform to the grid-tied inverter, and the grid-tied inverter would shut off. Now we've got the ability to adjust that waveform and basically disconnect the grid-tied inverter. We've also got the ability to curtail. So what do we mean by curtail? Part of the breakthrough in 1741 SA was that certification laid the groundwork for, I guess the best way to say it would be kind of advanced grid settings. And what I mean by that is you can program an inverter to do a range of activities based on the frequency or the voltage that it sees. So rather than a pure binary on or off, if the grid's qualified and I've counted for 5 minutes to make sure it maintains qualification, if those two things happen, then I will produce full power. The moment that the grid shifts outside of those parameters, either on frequency or on voltage, then I disconnect, and the grid-tied inverter would once it senses a qualified grid, would then have to count back up to 5. So in AC coupling, without this kind of advanced grid certification, you really had two states. You had on or off, and this presented a lot of issues. Now with frequency shift and active curtailment, we've got the ability to go from an on-off switch to kind of a potentiometer or a dimmer switch. We can adjust settings in such a way that the Radian, with the appropriate or the right kind of grid tie inverter, can run at 80% of rated capacity on that inverter. Could run at 60%. You can adjust multiple steps, and this allows you to do a couple of really powerful things. One, you avoid that kind of harsh on-off, which can be pretty impactful to the grid tie inverter. You can also throttle the grid tie inverter back down, which has advantages in both keeping the inverter on and not having to wait for that 5-minute count up. Also can allow you to do things like 3-stage charging. Can allow you to really fine-tune the system to what the batteries and the loads are going to want to see. So lots of really good stuff in here. I do want to correct one thing that I said earlier, and that was that prior to this new firmware, we really didn't have the option of adjusting the AC output from the Radian. So your options for AC coupling in the past with the Radian and the grid tie inverter were that you needed a disconnecting device controlled by the Radian. So because it couldn't alter that waveform, your choices when you wanted to AC couple like this was to use a relay driver that would, when, let's say when batteries were full, the relay would open, effectively disconnecting the grid tie inverter. Prior to that, you could use a remote operated circuit breaker, which was pretty cool in theory, a little clunky in practice. There were only a few suppliers that made these types of circuit breakers for this application, and they were fairly expensive. So while I would still recommend a relay in here for protective purposes, and mostly we talk about protecting the battery, you don't need that relay to execute the start, stop, or curtail commands. You can do all of that via frequency shift from this new firmware. So really powerful stuff. That's out now for Radian. You can download that off the Outback Power website. It's in testing for the Skybox products. It's firmware. How excited can we be? Well, pretty excited based on what this is going to allow people to do. So cool stuff there from Outback. So we've covered AC coupling. We've covered DC coupling. I want to get into the why, and basically the rest of the presentation will be about, how do you determine which tool you want to pull out of your toolbox? So pros to DC coupling. I would say typically better communications between inverters and quote unquote PV harvesting. So PV harvesting, that's kind of a nonsensical term. Josh, you made that up. Yeah, to try to compare apples to oranges here, I use the term PV harvesting so that we can compare a charge controller versus a PV inverter. So when I say better communication, in most instances on the DC coupled solar plus storage system, you're going to be running material of similar brands that can speak to each other through FlexNet, through ZAN bus, through kind of proprietary communication, and your inverter and your charge controller will work in harmony to make sure you're harvesting the right amount of power based on what your batteries and what your loads need to see. And we'll have some, this next point, we'll have a more in-depth explanation of this, but more efficient for non-concurrent loads. So when you are storing power for later, you're saving yourself a conversion cycle. That can be very important depending on the application and how, call it how aggressively you are, or your array. Generally speaking, a wider array of equipment available and pre-wired solutions for DC coupled systems. Cons, wiring can be expensive. We saw a couple examples where the first example, that off-grid installation in Laramie, the arrays on the roof, all of the power equipment and batteries are co-located. That's less of a consideration. If you think about an installation where your array is ground mounted, out where it can get solar resource, you've got long runs. If you've got really large arrays, wiring between the charge controllers and the batteries can be very expensive. Also, depending on what array voltage you're trying to use, wiring can be very expensive as well. I don't have a handy rule of thumb, but think about the cost increase of wiring at a similar amount of current at 150 volts versus 600 volts. Can add up really quickly, and really quickly can eat up any of the savings from a grid tied inverter versus a charge controller. Next con here is less efficient during concurrent loads, kind of as we would expect. And the last point here, flexibility on sizing inverter versus array versus storage. So this should probably be a pro, but when you're DC coupling, you've got you've likely got more options in sizing the array to the inverter to the storage. And the way I think about sizing is size your storage to your loads, to the backup you're going to need, times your days of autonomy. You're sizing your inverter to your maximum peak power you're pulling, and then you're sizing your array to to your days of autonomy there, as well as how much solar resource you have. So you see there with those three factors, you know, you could very quickly lead to lots of different permutations on inverter versus array versus storage, depending on your application, where you're located, what your load profile looks like, you know, how you vary your overall energy versus power in a given day. DC coupling can provide you a lot of different options for kind of picking the right sizing. So I talked about concurrent loads and round trip efficiency. Let's think about a couple different, you know, sample cases here. On the left, upper left, we've got an off-grid home in Wisconsin, USA. We see here in blue, that's overall load. We see in orange, orange, generator power. So when is that generator kicking on? And then we see in green, we see kind of overall MPPT power, so power from the array. We see here for the most case during the day that the loads, you know, the loads basically follow the generation. We've got some spikes here, you know, maybe sometime around noon, where we've got some, probably looks like appliances being run in unison. So we've got some instances where the generator will kick on during the day, but for the most part, except for these spikes here in the evening, which is probably, you know, dishwasher or entertainment. For the most part, the loads follow the production. That's an excellent example of a DC coupled system, you know, maybe not being the right approach. And I say that because as we go through the conversion cycles, you'll see that in a lot of those instances, a PV inverter might be more efficient. Down here at the bottom right, a much different case here. So the purple blocks will be kind of load profile through the day. And this has been unitized to kind of percent of total system size. But the loads are very low, you know, in the morning through the production cycle here in orange. The loads really don't start until the lights go down. And I don't know exactly what type of system this is, but you know, this could be lighting load. It could be cooking appliances. Could be a lot of things. But this is, in my opinion, you know, a better use for this would be a DC coupled system where in the conversion cycle to storage, we're more efficient, maybe a little less efficient in inverting from PV. So two different system sizes. Let's think about what the round trip efficiency is and DC coupled versus AC coupled. So DC coupled, generally speaking, most efficient when storing energy for off-peak hours. So when we're storing, we've got one stage conversion from the array down through the MPPT charge controllers right into the batteries. And we've really simplified this. We've taken out the wiring losses. We've taken out we're going to assume we're using the same battery. So we've taken out the kind of charge losses from the battery. So one conversion cycle from the MPPT charge controller, those are generally speaking pretty efficient, around 96%. Let's think about the flip side when we're consuming concurrently. So two-stage conversion. We're going from the array through the MPPT charge controller into the batteries. We're then inverting, and most of the inverter chargers out there are between 91 and maybe 94% efficient into the load. So when we are doing a two-stage conversion, you know, you're taking this 96 and you're multiplying it by 0.92, you pretty quickly drop down to 88%. On an AC coupled system, most efficient when consuming energy directly. So when we're, and I'll deal with this one first. When we're consuming in an AC coupled system, you know, it's essentially just a kind of a plain old grid tied inverter. We're going from the array PV inverter directly to power the loads or back to the grid. I say 97% here. It's an older slide. You know, these are now 98% and above. In some cases for large central and three-phase string inverters up to 99%. So much more efficient in an AC coupled system when you're consuming concurrently. less less efficient when you're storing for later. So two-stage conversion at that point, from the array into the PV inverter, into the battery inverter, and then into the batteries, 88% efficient. So you see here, we've talked about one of the big determinants for what's going to be the quote unquote best system is, well, when are you going to be using the power? Why AC couple? Let's walk through some pros here. Pros, as we just saw, much more efficient harvest and inversion when you're using power concurrently. Pros, higher voltage connection between the array is going to mean wire savings. So if you've got long runs, or if above a certain system size is really when it gets impactful. Think about not just the 6 kW system, but 12 or 18. When you've got larger and larger array, obviously you're gonna be taking those small unit savings and multiplying them over a larger array. More wiring savings there. Easiest retrofit. This is probably the biggest one we see when I talk to customers who ask about AC coupling. We're doing a retrofit. We're going back to a grid-tied inverter system that was installed 1, 2, 5 years ago. Homeowners gone through at least one outage where they realized the inverter wasn't going to do anything with the grid down, or maybe maybe they had always planned on introducing storage, or maybe their needs have changed and they want to introduce solar into the equation. And look, I get it. Like, the array's there, the inverter's there, everything's working perfectly. And also, it feels bad to say, here's this good equipment and I'm going to take this down and rewire everything. And I'm probably going to, either this inverter is going to, this PV inverter that we take off the wall is just going to gather dust in someone's garage, or we're going to scrap it. Like, that's not a real feel good, right? Like, it's, we're in the sustainability and renewable business. It doesn't feel good to take and scrap perfectly good equipment. So if that's the case and it's a retrofit, AC coupling is, you're probably going to lean that direction. If curtailment is enabled, so if you've got the new firmware from Outback Power on your Radian, or you're doing frequency shift on a Schneider Electric XW Plus, and you've got a grid-tied inverter that can take inputs from those signals, can be a very elegant solution. Cons. So this is hands down the biggest one historically that has hamstrung this application is uncontrolled charge currents. So uncontrolled charge currents occur in an AC coupled system with no grid present. So you take away the grid, there's nowhere for excess power to go except into the batteries. If you don't have curtailment equipped, and your batteries are not sufficiently large to handle an extra, 10 amps, 25 amps, whatever your PV inverter is producing at full tilt. When there's no loads and your batteries are full, those are amps that have nowhere to go. So AC coupling's almost never recommended when in a pure off-grid application, unless you're going to do some very trick things with diversion loads, etc. I would say this has historically been true. The second one, fewer approved options for storage inverter. So, I think we're starting to see a little more flexibility now from inverter suppliers on, really approving of this application and designing firmware specifically for it. Third con here is going to be reduced flexibility on system sizing. So I'll speak to this on the next slide, but generally speaking, in order to protect the batteries and protect their equipment, most storage inverter manufacturers recommend no more than a 1-to-1 ratio of PV inverter to battery inverter, and in most cases it's more like 3 to 4, not 3 to 4 to 1, but 0.75 to 1 or 0.8 to 1. So that can reduce your flexibility on kind of tweaking the array versus inverter versus storage sizing. I'd say the last thing here on the AC couple, and it's not specifically called out, but one of the things that has really led to bad installer and homeowner experiences is AC coupled with very small battery. So if you're designing the system on a budget and your intent is only to present a qualified grid for the PV inverter to keep working to power loads during an outage, I can see a case where a lot of installers would say, oh, I'm only going to need 100 amp hours. All I'm really trying to do is make sure that battery inverter stays on so that I can keep harvesting. That's an example where it goes back to my first point here on uncontrolled charge currents. Really small battery, great. I keep the PV inverter running. I keep producing power. When the grid's out, what happens when you turn the TV off, the refrigerator cycles off, there's no loads? The battery, that current's got to go somewhere. When you're using really small battery banks in an AC coupled solution with no grid, you're going to have a bad time. That battery's it's going to kill itself. If you've got a 100 amp hour battery and you're regularly presenting it with 10 or 20 amps of uncontrolled charge current, it's going to have a really short life. And we don't want to think about batteries as disposable. We want to size the system properly the first time so that A, your homeowner has a good experience, and B, you get the most life out of your battery bank. So speaking here about curtailment, why is this important? In sizing an AC coupled system, we talked a lot about uncontrolled charge currents. Rather than kind of belabor this point, just want to speak to an experience I had when working with one of the solar decathlon teams, about 6 years ago. University of Tennessee had built this beautiful solar decathlon home. It actually had cylindrical tubes on the roof because they were really going for an aesthetic look. Basically had 10 kilowatts of array, and I think they put it on those were on two 3.8 kilowatt PV inverters. They did well at the competition, didn't win, but did really well. Then they wanted to take this thing on the road. They wanted to kind of go on a road show and get this out in front of Tennesseans and, really see what this stuff could do. Now, obviously, they're going to go out on the road. You're not going to have an extension cord capable of supporting 200 amps that you can just plug in anywhere. So they knew, okay, we're going to need to add storage to this. We're going to need to add a battery inverter. They were really hamstrung on both budget and storage space. If you've seen these homes, they're pretty small. So they're really kind of pigeonholed on budget and storage space. They put in a battery inverter and a really small battery bank. The end result was that on sunny days, the batteries would top off very quickly. The system would power loads for a period of 20 to 30 minutes. The battery would drop to back into the bulk stage. The battery inverter would then try to tell the PV inverter to start up again. 5-minute count up. Sends out a qualified grid signal to the PV inverters, and those guys have to wait 5 minutes as required at that point by UL 1741. That 5 minutes waiting for the PV inverter to start up would basically drop that bank below low battery cutout, and the whole system would power down. So as our application engineers worked with this team, they really presented them two options. You can add more battery, which they really couldn't do based on the size and the budget they had to work with, or you can have less PV. So what they ended up doing was disconnecting one of the PV inverters. They've now got a smaller system. They've got less autonomy, but they've better sized the PV inverter to the battery inverter. The battery would take more time to kind of charge up all the way, but they've now done a better job of sizing array to inverter to battery, and they could operate it in kind of steady state at that point. So really what we ended up doing there is, really similar to what we have here. Grid, AC panel, well, no grid, but AC panel with loads, inverter charger, battery, PV inverter from array, AC sub panel. When the system is curtailed, when the grid is down and there's no system from PV, you're still sending a qualified grid signal to the in this case Sunny Boy inverter. In curtailment, you're tweaking that signal that the PV inverter sees so that you can operate at 80% of rated power or 60%. SMA really got onto this first. They had for a long time on their Sunny Boys, and they may still, a mode called basically off-grid mode. So what this did was it would disable the 5-minute count up on 1741, and it would take inputs outside of that kind of standard 60 hertz. So you could operate at 62 hertz and it would throttle down. Similarly, if you went to 63, it would throttle down further, and then finally it would cut off completely at 64 hertz. So it really kind of led the market on this. In a lot of ways, that off-grid application in their firmware, kind of became the basis of 1741 SA. So really ahead of their time on this, ahead of their time on the Sunny Island as well. Yeah, it was a really good system for a long time. A little on the expensive side, but a lot of benefits to that system. So let's try to kind of put a bow on everything we've talked about today. System considerations. What are some things that are going to lean you one way or another on AC versus DC coupling? Primary application, backup versus self-consumption versus off-grid. How the system's being used is really going to impact, your considerations on a lot of other things. But in a pure off-grid situation, in my opinion, you're going to want to take AC coupling off the table. Self-consumption, meaning a lot of concurrent use, or maybe not concurrent, but daily cycling, backup. Those are things that are going to help you determine not only AC versus DC coupling, but also what type of storage you're using. Battery type. Will the chemistry support high charge currents when the system is islanded? Some batteries are, more agreeable to that than others. Sizing rules. So, your ratio of PV inverter to battery inverter. And as I mentioned, at best, at its most aggressive, you're going to want to do no more than 1 to 1. In most cases, you're going to want to do like 0.75 to 1. So if you're thinking about an 8 kW radian, no more than 6 kW of PV inverter. On a 6848, you're probably going to be 5 to 6 kW PV inverter. Location of array versus power equipment. Co-located, okay, maybe DC coupling is a fit. Long run, it's really going to steer you towards an AC coupled solution. Last point here, warranty of PV inverter when AC coupling. So a lot of bad, call them horror stories out in the market on people who ran an AC coupled application, had some issues, and called their PV inverter manufacturer and found out that was not a supported application. They've written down my serial number and now my warranty is void. That's one of those things you're going to want to check on, maybe through message boards, maybe through forums, maybe through hypotheticals with your manufacturer before you design and install the system. So lots to consider here. Now we've covered AC versus DC coupling, and I don't want to further complicate things, but on really large systems, you've also got the ability of doing both. I've seen some plan sets for some really large off-grid systems in places like Africa and Australia, where you may determine that on a 6 battery inverter system, you're best using a combination of DC versus AC coupling. So think about the DC side, the DC coupled side of the system. You're going to size that to run non-concurrent loads. You're going to size that to store for evening and morning startup. You may size your AC coupled portion of the system to run the loads concurrently. So think about, I'm going to size my AC coupled portion of the system to run all my daytime loads, and really minimize the amount of energy from that AC coupled portion of the system. I'm going to minimize how much of that I anticipate going into the battery. So some really complicated stuff here that you're probably going to want to use a system like Homer to build out and model, but just wanted to say that's available. That's an option on the really large side. In my opinion, not recommended for a system less than, probably 18 or 20 kW of inverter. You're going to spend a lot of time designing and engineering something that, you may spend a little more on the product, but will be simpler to install and troubleshoot and diagnose. So what products do we have out there to fit these things? DC coupled from Magnum. You've got the their full lineup of MS inverters. Outback. Now we've got Skybox, we've got Radian, we've got FXR. From Schneider Electric, we've got XW Plus, we've got XW Pro, we've got SW. Assuming you don't need to do cell mode there on SW. AC coupled from Magnum, you've got their GT500 and 600 microinverters. AC coupled from Outback, basically the full range of equipment here. I threw the GSLC in there because it's really recommended for AC coupling. You can put all of your circuit protection in there, and I've got the older version. The newer version is, in my opinion, much more conducive to wiring and kind of practical application of people with real sized fingers. The older version was pretty tight in there. Similarly with Schneider Electric, you can AC couple with XW Plus, XW Pro. Probably wouldn't recommend it with SW. So wow, it's 9:53. We've covered a lot of ground. Got a little bit of time for questions. As always, here's our email link. I've got 3 really qualified folks who can help you with designing, kind of, I don't want to say anything and everything, but, most practical applications they've seen dozens and hundreds of times. Our phone number as well. So lots of ways to get a hold of us. Caitlin, we've got a few minutes here for questions. Have we had any good ones come in?
Yeah, thank you, Josh. So I'd like to go ahead and start off the question and answer session now. If you have a question, please go ahead and submit the questions through the question pane located on your control panel. And again, we'll try to answer as many possible questions as we can. You can always exit the webinar during or following the question and answer session. A brief survey will pop up once the webinar ends. Give us your feedback and I'll go ahead and send over the presentation to you. So David is wondering, what do you recommend for a 300 kilowatt off-grid system, 3-phase, 60 hertz, 480 volt with 400 kilowatt BESS with 100 kilowatt diesel generator backup? Sorry, that was a lot of information there.
Wow, that's like the Binford 6100 of off-grid systems. All you home improvement fans out there. The simple answer there is there's very little product that's readily available over the shelf for something that large. Generally speaking, anything over really 60 to 70 kW is going to be a custom engineered solution. Maybe not fully custom, but you're going to be in the Ideal Power, Princeton Power, kind of Cummins generator sort of world. There's equipment that can be coupled up into systems that large, but frankly, it's not anything that we've got access to. Your best bet is to reach out to someone like Princeton Power and see what you could put together. I would love to see something like that, but those are few and far between.
I'm interested to know what type of project it is. So,
yeah.
John is curious, now that the new Sunny Boy inverters no longer support curtailment, which grid-tied inverters is the new Radian software designed to support?
Good question. So I was not aware of that from Sunny Boy, and it's a little surprising, frankly, because with the new SA hardware, it's essentially what grid operators will ask those inverters to do. So through the use of local grid profiles, and I'm a SMUD customer, so let's use SMUD as an example. When the grid frequency or voltage drops, when the frequency or voltage drops, they're going to want the inverter to maintain full rated power. When the frequency or voltage rises, they're going to want that inverter to actively curtail. They're not going to want that inverter to shut off completely, because as the grid gets more and more saturated with PV, saturated is a bad word, but as we get more and more PV on the grid, if you think about an event where the frequency rises to 62, and then, you know, in an afternoon, 5 to 10 to 20% of that generation drops offline. That's a really bad event. That's really taxing on the grid. So the reason a lot of these standards came to light was areas like San Diego and Hawaii, where grid operators knew they would have to have a way to keep most of that PV generation online, but maybe throttle back. So I do want to check in with SMA on that, because it's my understanding that they will film it. You may need to modify the grid profile settings there, and maybe not right out of the box what we want it to do in an AC coupled curtailment situation, but I'd be very surprised to learn that they've removed that functionality completely.
All right. Well, I want to thank you, Josh. That concludes our question and answer portion of the webinar. Thank you all for joining us. And join us May 10th for a new product showcase. Always check out our website for more training opportunities with AEE Solar. Have a great weekend, and thank you for doing business with AEE Solar.
Thanks, everybody.